this video, we are going to start introducing a geometric point of view on special relativity. Looking at the special relativity from a geometrical point of view is extremely useful. This is a path that was started by Minkowski when he defined Minkowski spacetime. And at the beginning, Einstein was not very happy with it. He said that people had rewritten his theory in a way in which not even himself could understand it. But in due time, I think he realized that geometry is a very, very powerful tool, not only in this area, but especially in this area. And it was this geometrical point of view that allowed him to get to general relativity, which is really a theory of geometry in a larger space. So let us start by introducing some concepts. The simplest concept and the principal concept at the same time is that of space-time. At the beginning, these concepts are going to be just intuitive, not very rigorous, and little by little we will revisit them and we'll make them more rigorous, okay, up to the level of this course. So space-time is just the set of all events. All events, each event will be a point in this space-time and is something that is labeled by a time coordinate t and some spatial coordinates xi. Here I am going to use units c equal to 1, so t and x0 are exactly the same. The next thing that I'm going to introduce is the interval. Between two events. And now this concept requires introduction of other concepts. So for instance, for first we are going to introduce this delta x mu's, which is the difference between the coordinates of the event 1 and the event 0, and which we are going to call vectors. Okay, this is similar to what we do in standard 2 dimensions, for instance, in which we have 2 points and we have the vector that joins them. Okay. As I said, this is not extremely rigorous, but for the moment this is okay. And we need also something called metric. So what is a metric? A metric is a real, so gives you real numbers, something that gives you real numbers. Symmetric this means that there must be this has to act on pairs of things, and that the order of these things of the pair does not really matter. And bilinear form, which acts on vectors such as, for instance, but only for instance because it is really more general than it cannot be applied to more vectors than just this delta x mu's. Okay, so it is something that we will write G that acts on vectors. Let me call these vectors V and omega. These are 4-dimensional vectors in this 4-dimensional space-time. And it is real, so the result will be a real number for any V and W. It is symmetric, which means that it doesn't matter if it acts first on omega and then on V. Okay, and it is bilinear, which means that if I make a linear combination with real numbers, then I get a linear combination of this product, if you want. Okay, This metric is also called scalar product of V and omega. Okay, it's a real number which is given by this form, and it doesn't depend on the order. It is bilinear and so on. So it really, this bilinear form describes a scalar product of two vector fields. We can define the interval between two events by just the value that takes this bilinear form, and you evaluate it on these vectors that join the two events in four-dimensional space-time. So this is just by definition. Okay. Now any bilinear form like this one has a matrix associated that whose components we just called G mu nu, in the same basis in which these vectors have components V mu and omega mu. So the property of this matrix is that if we want to compute G of V and omega, this is given by this, where the sum is as usual assuming mu and nu. Now, because this is symmetric, this is G mu nu, omega mu, V nu. Now observe that here, sorry, this should be omega. These indices mu and nu do not have a particular meaning. We can replace them by something else. So I can replace, for instance, mu by nu and nu by mu. It is exactly the same. So this would be G nu mu, omega nu, V mu. Of course, these are just numbers and commute, and I can write them in any order I want. Now, if I compare these two expressions, what I find is that the symmetry in the arguments translates into a symmetry of the components. If I interchange the first and the last component, or the first and the second in this case, this is the same. Now, if I write this G mu nu, the set of G mu nu's as a matrix, and so on, G1, 0, G1, 1, so on, and here. Okay, you see that mu, by convention, labels rows and nu columns. It's not mu and nu, it's really the first index, by convention, labels rows, and the last index labels columns. So if I interchange the indices G mu nu as here, what I'm doing is taking the transpose. Let me put it in this way. Suppose that I call this matrix G, and what this is telling me is that G is equal to G transpose, because the components of this one are G mu nu, and the same components transposed are G mu mu. Okay. So this is a symmetric matrix, and the expression in components is this one. Now, what is the Minkowski metric? This is a particularly important metric which gives us a particularly important interval. And this is our old friend eta, okay, whose components are, okay, these parentheses mean that this is the set of all the components, which we order as usual, eta 0, 0, eta 0, 1, etc., eta 1, 0, blah, blah, blah. and that in Cartesian coordinates takes the values 1, minus 1, minus 1, minus 1 in, and this is important, this is my convention, known as the mostly plus convention, sorry, mostly minus convention, because there are more minuses than pluses in this diagonal. The elements, the components that I haven't written, take the value 0. So this is the Minkowski metric that gives us the interval of special relativity. But of course, we can consider other metrics. Just one word, the same metric in different coordinates is still the same metric. Okay, we still don't know very well how to change coordinates. We just changed to from Cartesian to Lycon coordinates, but we will do more complicated things, and it will still be the same metric but in different coordinates. So we can make it, we can do a special relativity in different coordinates, but always, because it is a special relativity using the Minkowski metric. Now, Minkowski space-time is space-time endowed with the Minkowski metric. This space-time that we have introduced at the beginning, since it is just defined as the set of all these events, and all these events, all the events labeled by these four numbers are real numbers that can take positive or negative values. This is just R4. So Minkowski space-time is R4 endowed with the Minkowski metric. One word of caution before we go on. We are using these vectors or that join two events which can be as separated as they want, and we are using the interval that by convention is written in this way. Okay, this ds square means stands for the interval, sorry, it's delta x mu, and here there are no problems because in Cartesian coordinates that we are using, eta is constant all over the place. It has the same value anywhere. I haven't said that if this is true for in some region of R4, or it is true in any region of R4. But suppose that this is we are using some coordinates in which the expression of eta mu depends on the point. Then we have a real problem, because how do we evaluate this? Okay, let me call at this stage this is only delta s square, so this is the interval square. So this if eta depends on x, where should we evaluate this? At which point? At one of the two events, in the middle, on average? The only good way to do this is to define this interval infinitesimally. And this is where I should have used this ds square and use points which are consider only events which are separated infinitesimally one from each other. So basically they are essentially the same point. Okay, the difference is infinitesimal. We all know that this is not mathematically rigorous, but it works. And they are, you can just take the point x, because the difference between x and x plus delta x will be too small, because this is multiplied already by delta x. So this is what we will have to do. We will have to go to an infinitesimal version of everything the moment we consider metrics that depend on x. This can, or Minkowski metric in coordinates in which they depends on the components depend on x. So this will be true for any metric. We will have to do this, and this will be the definition of the interval. Meanwhile, okay, and still in Cartesian coordinates, the interval that we have, okay, let's call it the special relativistic interval, or the Minkowski metric, because one and the other are in one-to-one relation, is not positive definite. This means that if you evaluate d on the same vector vb, this can be larger than 0, smaller than 0, or equal to 0. In fact, we haven't demanded anything about this, and as a matter of fact, it is easy to see that the Minkowski metric can give you positive, negative, or 0 values, depending on delta x mu. So if eta delta x, remember that this is just eta mu nu, delta x mu, delta x nu. If this is positive, okay, and this means that the most important component, the part that will weight more in this calculation, will be the one associated to this positive number, and this is in the x0 direction, which is the time direction. Okay, so if this is positive, we will say that the interval between these two events is time-like. If it is 0, we will say that it is light-like or null. And if it is negative, we will say that it is space-like. I'm sure that you know very well the meaning of this, but we can draw it in a space-time diagram. Okay, well, this is x1 and this is x0, and suppose that the event x mu 0 is 0, is at the origin. Okay, so we know very well what light-like or null is, because this means that there is a light ray that crosses the point x mu equals 0, and also the point x mu 1. Okay, so all the points related to the origin by light-like or null interval are really points that can be joined by a light ray. You know that in this diagram, okay, if you only have two directions like this means that delta x0 square is equal to delta x1 square. So then they can be positive or negative, the relation between delta x0 and delta x1, and it means that light rays can propagate for the positive in the positive direction of delta x1 or in the negative direction. While all these points that can be joined with the origin by light rays are the light cone. If you have more dimensions, then you have a circle at each point. Okay, you will have more circles here. Okay, so this is really a cone, and if you add a third spatial dimension, you could have, instead of circles at each point in this cone, you could have a two-sphere, which is much too difficult to draw, for me at least. Okay, so this light cone separates the region of the points or the events that are related by time-like intervals with the origin, okay, and which lie inside. This means that if you go from here to here, so this is your delta x0 will be larger than delta x1, okay, in absolute value, and it depends, and you lie inside of the cone, and this corresponds to something that propagates at a speed lower than the speed of light, or that comes to here in the same way. Space-like separated events lie outside of the light cone, okay, and to go from here to here, your delta x0 has to be smaller than delta x1, and in order to do this you have to move at the speed faster than the speed of light, so you would say that this is just a space separation, okay. It doesn't correspond to the motion of any known physical particle. This means that in space there are causally disconnected regions, okay? So you will never ever, if you are here, you will never ever reach this area, the whole exterior of the light cone. This is an advance of what will happen in black holes, of course. Another property is that not only it is not positive definite, this interval, it is also, it violates the triangle inequality, sorry. Okay, if we take this, the interval between events 1, 2, and 3 as a distance, let me write it like this. So this would be the interval computed with the Minkowski metric between the points 1 and 2 and the points 2 and 3. When a point and event are the same thing, this is not larger or equal than the distance between, or the interval between 1 and 3. Let's see this in an example. So we go back to a space-time diagram. And let's draw event 1 is at the origin. For convenience, we can always do that. We know it because we just sorry, before I join any line, let's consider, let's write the light cone. Okay, so suppose that point 2, event 2 is inside of the light cone, and event 3 is back on the is also in the interior of the light cone, but it is also at x1 equal to 0. So now let's consider the triangle that joins these 3 points. Okay, you can go from 1 to 3 just by not moving and just letting time evolve, or you could go first from 1 to 2, moving at whatever speed, okay, and then from 2 to 3. And if I draw this 1, this okay, because you see that the angle here lies outside of the light cone that I would draw at the point 2. So let me redo this again. Okay, so this would be, in order for this to be physically possible, we have to write event 2 here and here. Okay, now if I draw here the light cone at the event 2, this line that goes from 2 to 3 is inside of the light cone. So this corresponds to time-like intervals. Now, from 1 to 3, you only have delta x0 because delta x1 is 0. This is a time-like event. From 1 to 2, you have delta x1 and delta x0. And you see that if you go fast enough, you can go very close to the line, to the light cone, which means that delta x0 will be as close as you want to delta x1. And this means that the distance between 1 and 2 will be as small as we want. Okay, not 0 because we would have to go at the speed of light, but okay, you can even consider, if you want, the motion of a light ray instead of the motion of some body. Okay, and from 2 to 3 we can also find a 2 and a 3 which are joined by an interval which is also as small as you want. Okay, however, so this will be as small as you want, d12 and d23, but clearly d13 has the value that it has. It cannot be made smaller, and this inequality is violated. Okay, the fact that this is violated is at the root of what is called the twins paradox. But we need to introduce the notion of proper time and word line, etc., of an observer. For the moment, it's just enough that is to see that this is not satisfied for this interval. Okay, so let's go on and let's introduce a word line. Okay, this is usually the word line of a particle. Okay, and here light is considered a massless particle. So it's the trajectory of a particle in space-time. So usually it's described in some reference frame, which you have coordinates x mu, as a function of some parameter, some real parameter. So in space-time, okay, here this is two-dimensional. This describes a curve. Okay, when you go along all the values of lambda. Then, okay, we have first classification of possible word lines. I mean, if you see this word line that I have drawn here, it doesn't look like the word line that a physical particle can have. Why? And because, okay, if you look at small okay, points of this curve and you draw the tangent, which is an approximation, okay, or the infinitesimal version of the this vector that joins 2 points. So I divide this by this, and I take the limit lambda going to 0. Then I have a vector. Okay, this is always a vector. I am dividing these vectors by a number. So I get the tangent to the word line at a given point. Okay, I compute this. I say, sorry, it's delta lambda that goes to 0, but I compute this at a certain value lambda, say lambda 0, that is over here. Now this vector has to lie inside of the light cone at this point, at the point x mu of lambda 0. This is the point. Okay, for the value lambda 0, you have the particle is at the point x mu lambda 0, and it has this tangent, and this tangent being this limit, okay, dividing by a number does not change the angle that this vector forms with the light cone, so it doesn't really matter. The only thing that the size of this vector doesn't really matter. The only thing that matters is the angle, so it either lies inside or lies outside. So for physical particles, the tangent to the word line must always lie inside or over the light cone. At the point at which this is computed. So So it is inside. If the particles have mass, because massive particles cannot propagate at the speed of light, they always propagate at lower speeds, and over if these are massless particles or light. So a physically acceptable Or line would be something like this. Okay, this could be something like this. Maybe here, well, okay, it would have to be something like this. Now, how do I know if this tangent to the wall line lies over the light cone outside or inside? Okay, since this, which is really just the derivative of x mu with respect to lambda taken at lambda 0. This is a vector, okay? I can compute with the metric that I have this thing, okay? This is not the interval, okay? It's close to an infinitesimal interval, but this divided by this lambda, d lambda squared, but it doesn't matter because the value does not really matter. It only matters if it is larger than 0, equal to 0, or smaller than 0. So these are the three possibilities. If this is larger than 0, this tangent vector is time-like. This is equal to 0, this is null, and if it is smaller than 0, it is space-like. And then what you want is that this thing is either larger than 0 or equal to 0 for all values of lambda. The next thing to consider with word lines is how to choose the parameter lambda. The way I have described it, lambda is just a convenient parameter. It has no physical meaning, but of course we can choose parameters which do have some physical meaning. There are several principal choices. The first choice is the coordinate time. This means that I am choosing lambda to be x0 all the time. Okay. Then the rest of the coordinates of the wall line, or the rest of these functions, are just functions of x0, or in units in which c is equal to 1. This is just t. Okay. This is the standard parameterization in Newtonian physics. Okay, but there it is natural because there is only one t in all reference frames. In special relativity, this is referred to the time, to the coordinate time at a given inertial reference frame. But clearly this is a convenient parameter. Another possibility, which is new in special relativity compared to Newtonian physics, is the choice in which lambda is the proper time. Okay, it is the proper time, which is usually denoted by tau. I will also denote it by s, although this suggests time and this suggests the space. Okay, and this is because when if the word line is the word line of a particle, I usually talk about the proper time. But suppose there is a word line which is not physical and it is space-like all the way. Okay, then it would be proper space or proper distance, something like that, and I could use s. But many times I use any of them and I don't really care very much. Okay, this parameter, whichever of them you prefer, is characterized by the fact that for time-like or lines, This means world lines whose tangent vector is time-like everywhere. When I compute this scalar product of the tangent vector with itself, but expressed in this using this parameterization, okay, I get 1. The fact that it is time-like means that in general this is just positive. Now I choose a particular lambda, which I call S or tau, and which is characterized by the fact that this gives me not just any positive number, but gives me precisely 1. Okay. The physical meaning of the coordinate time is clear. It is the time that one observer, which is sitting at rest at the origin of the coordinate system, measures with its clock, the clock which is attached to the reference frame. So what is the physical meaning of the proper time? So I'm going to argue that S is the time that an observer commoving with a particle would measure using its own clock. An observer commoving with a particle means that the observer is at rest in a reference frame which is carried by the particle. This reference frame is one in which, for instance, the particle is always at the origin and moves, if possible, with its axis parallel to themselves all along the way. Before I prove this, I need to show something else. First of all, this definition that I have made is not clear if it depends on the coordinate system in which I am working. So this assumes that I have parameterized my world line as x mu of S, and these x mu's are coordinates in a reference frame, which is an inertial reference frame, so that the metric is eta mu nu. Okay, this definition of proper time can be generalized to any other frame and any other metric, but for the time being, let's just consider inertial reference frames. What happens if I try to compute S or find S or write this condition that defines S in another reference frame? Well, if it is inertial, it will be related to x mu, the coordinates of this reference frame, will be related by a Lorentz transformation plus a space-time translation. So when you compute the x prime mu ds, you find that only a Lorentz transformation acts on these guys, and then you introduce this here, and okay, you are going to find that the x prime mu ds eta mu nu dx prime mu ds is equal to the x rho ds lambda mu rho eta mu nu lambda mu sigma d sigma ds. Okay, but by definition, if this is a Lorentz transformation, this gives eta rho sigma, and then with this definition, this is also equal to 1. So this parameter clearly has a meaning which is invariant under Poincare transformations. The fact that it measures S is not just independent on the inertial reference frame, but can be computed using any other parameterization, because the interpretation, apart from the interpretation that it is the time measured by a commoving observer with the particle, is that S is the invariant interval between x mu of S and x mu 0. So suppose that this is the initial point and this is the final point. Okay. This particle moves in this way, and at s equals 0, okay, it's at the point with coordinates x mu 0, and we are going to show that at the value s, this is x mu 1, and what I want to show you is that this s is precisely the value of the interval integrated along this whorl line. So first I write s in this trivial way as the integral between 0 and s of differential s. Then of course I can always multiply by 1, and this 1 can be the square root of this expression. So I integrate this between 0 and s, and this is the x mu ds eta mu dx nu ds. But suppose that I want to use any other parameter. How do I change parameter? Well, I replace s by some function s of lambda of the new parameter lambda, and I just change coordinates. So now I have an integral between 0 and s. Now s of lambda. Okay, now I will say what it is more precisely, and here I apply the chain rule, which is one of the fundamental tools of this course. And here we have ds d lambda, and you can see that these three factors cancel, and we have an integral which has the same form. So this would be lambda, okay, some value of lambda that gives you this s. So you can compute it using any parametrization, and you can also compute it using any inertial reference frame. Having proved this, we can now consider a particle moving with uniform motion, so the comoving reference frame is an inertial reference frame. And if it is a comoving frame, let's say that this comoving frame has coordinates y mu, and they are related clearly to x mu by a Poincaré transformation, and if we parameterize them by this proper time parameter, then we can write by definition equal to 1. Okay, this is the definition of S, and we have shown that this S is the same if I compute it in any inertial reference frame. So it is in particular, this is true in the system Y. But the definition of comoving frame is that there is no motion, okay, there's no spatial motion. So this will be some constants, and these constants I can set to 0 for convenience. It doesn't really matter. What matters is that if these are constants, then dy ds is always 0, and the only contribution to this expression is dy0 ds dy0 ds eta 0 0. This is the only component, because in these sums the y, I, and j, they give 0. Okay, this is equal to 1 and this is equal to 1. So we have dy0 square equal to ds square. And the conclusion is that y0 is s plus a constant that can be fixed. So the origins of the proper time and the coordinate time of the comoving frame are the same. So the proper time, the coordinate time of the comoving frame is identical to the time that a comoving observer would measure with his clock, and this is exactly the meaning. So in one of these problems in which the twin paradox problem, if you want, okay, so this is part of the light cone, and we said that we fixed 3 events, 1 at the origin, 2 and 3, which is also at the origin of the spatial direction, but it's later. Okay, now we know that the interval, the invariant interval between 1 and 2 would be identical to the time that a traveler would measure in its own watch if it moves at constant speed. This is why I drew a straight line moving from 1 to 2. So you send somebody with a rocket, and the time that its own watch would measure would be the invariant interval between 1 and 2 that we wrote the equal 1, 2. But it would also be the difference if we parameterize this by the proper time could be the value of the parameter s at 1, s at 2 minus s at 1. That would be the time that it would take for him measure with his own watch to go from 1 to 2. Now the time that it would take to go from 2 to 3 is s3 minus s1. And okay, the total time is clearly s3 minus s2. And this can be, we showed that this can be made as small as possible. So the twin paradox is, consists in somebody sending its own twin brother on a rocket at a given time. That this is, suppose that we fix the origin at the place where the rocket starts, and one of the twin brothers remains on Earth. Okay, suppose that he doesn't move, and the brother goes some way until point 2, which is some distance x1 here. It takes some coordinate time to do this traveling, and then returns to Earth, okay, to the point x1 equal to 0 at a later time. By the brother who stays on Earth, okay, lives in this coordinate system, and for him, because this is his own comoving reference frame, the time that he measures would be all this, okay, the difference between x0 at the point 3 and x0 at the point 1, the difference in coordinate time. But the twin brother would have a different perception, okay, his own clock would measure s3 minus s1. And we have said that this we can make as small as we want. In fact, by moving these two as close as possible to the speed of light, we can arrange this so this is almost 45 degrees also, and this is almost 45 degrees. You can make it almost 0. So the twin brother would return having a perception that he has less years than the brother that stays on Earth, and this would be true. It's not just a perception, it's something that clocks measure, and that would reflect in the biological age of both brothers. Is it a paradox? Well, it is strange, it is different to our perception, so it is a bit shocking, but it is something which is consistent. There is no inconsistency in this supposed paradox. Okay, some people argue that since one of the brothers, well, the brother that travels at constant speed, which is not true, because you see here there must be some acceleration. This perception should be symmetric. The brother who stays, because they argue that it is not possible to know who stays and who travels. Okay, because in the system of the traveling brother, he's always at rest, and the other brother that moves. But clearly there is no symmetry in this problem, because one of the brothers always has to undergo some acceleration, and the other brother does not undergo any acceleration, and that's the real difference, and this is what produces different results for these two brothers. It is impossible for the brother who travels to return without doing some acceleration, so this is always there, and this is the reason behind the asymmetry in the proper times that these two brothers measure when they join again at 3. Another interesting point of the proper time is that okay, we said that they can be computed using any parametrization. So in particular, we can use the coordinate time parametrization. And in the coordinate time parametrization, okay, we have, excuse me, so this is dx mu, dx0, dx nu, dx0, eta mu, dx0. Of course, you have to fix the limits of the integral properly in order to get s, but here we are concerned with the integrand only. Okay, so for mu equals 0, this is 1, and for the rest of the components, so dx0 is obviously 1, and the xi dx0 gives us the speed that we wrote as ui divided by c, but here we are working with unit c equal to 1. So this integral becomes the square root of 1 minus ui, which is just u square dt. Now next we expand for velocities much smaller than the speed of light, which in these units is 1, and this is 1 minus a half v squared dt squared. Okay, if you know what the Lagrangian of a free particle is, you could recognize up to the factor of the mass this as this Lagrangian. Okay, I don't know whether I wrote the t squared, but it's just dt. And this is a constant that can always be removed, not from this integral, okay, but if this is the action, which will be defined as the time integral of the Lagrangian, we can remove it. This is maybe a bit soon, maybe now, but we will in a few days remember this result, okay, and we will use it because we are going to study mechanics using Lagrangians and actions.